Okay, so we're going to solve the problems for the first discussion. And we will start with the review problems from Calc 1 and Calc 2. We have two simple differentiations and two simple integrations. So let's start by taking the derivative of the function f of x equals x squared plus x minus 1 over x cubed plus 3x. Here we need to use the quotient rule, according to which the derivative of u over v is u prime times v minus uv prime divided by v squared. So if we apply this, we find that the derivative of f of x is 2x plus 1, derivative of the numerator, times the denominator, x cubed plus 3x, minus the numerator, x squared plus x minus 1, times the derivative of the denominator, which is 3x squared plus 3, over the denominator square. Let's go to the next problem. We have the function g of x equal to ln of x squared plus 1. Here we're going to use the chain rule. The chain rule tells us that if we have a composite of two functions, let me use different letters here, so f of h of x, and we want to find the derivative, then we take the derivative of the outer function, which is f in this case, composed with the inner function, h of x, times h prime of x, times the derivative of the inner function. So here, our inner function is x squared plus 1. So it's really like looking at ln of y. So what is the derivative of ln of y? 1 over y. So we don't really write y, we write 1 over x squared plus 1, and we multiply by the derivative of what we designated as y, meaning the inner function, which is 2x. Next, we have a definite integral, the integral from 0 to 2 of x cubed minus x dx. Here we need to find an antiderivative, which is x to the fourth over 4 minus x squared over 2. And we need to just plug in 2 and 0 and subtract. So we will have 2 to the fourth minus 2 to the fourth over 4 minus 2 squared over 2. This can be easily simplified as 4 minus 2, which is 2. And the last problem is an indefinite integral where we need a substitution. Substitution will be u is equal to x squared. Formally, we write the u is equal to 2x dx. We don't have that too, so if we want to make our life easier, we will just isolate x dx, which is 1/2 du. And here's your x dx. So this will become e to the u, and now I need to write 1/2 du. I can put the 1/2 in front and just write the du, and this will give you 1/2 e to the u plus c. Okay, don't forget to go back to your original variable, which will give 1/2 e to the x squared plus c. Okay, and with that, we're done with the review problems. So let's go to our problems from week 1, which are really problems on vectors. And the first problem says it's not really a problem that can have a unique answer. It says simplify the expression 3ab plus 2ca plus bc as much as possible, where a, b, c are 3 points on the plane. They don't really need to be on the plane. They could be in 3D space. The truth is that since there are 3 points, they do belong in a plane. And all we want to do here is really play with the vectors. I mean, one might argue that this problem doesn't even have a definite answer. One might say, you know what, this expression is simple enough for me, I'm not doing anything. And that could even be an acceptable answer. But let's just discuss what is going on here. And what is going on is we really want to understand the addition of vectors through this problem. So if you have 3 points A, B, C, and basically what we're saying here is that the vector AC can be written as AB plus BC. And this is what addition of vectors is all about. So what we want to do here is play as much as possible with this concept. And I'm not even going to follow what you're going to see in the answer key. I will just play a little with it. And pretty much what we're saying here is that you can interpose any point you like. So I will interpose the point C here in AB. So I will write AB as AC plus CB. Again, this is a direct consequence of how we simplify vectors. I'm sorry, of how we add vectors. And now we can combine 2AC AC plus 2CB plus CB. So I'm breaking up this 3AC and 3CB that I have. And of course, I have 2CA and BC, and I have several cancellations. So 2AC cancels with 2CA, and CB cancels with BC, and we're left with AC plus CB, plus 2CB. Again, one could leave it like that, or we can even write AC plus CB plus CB, and AC plus CB is AB. So this will be AB plus CB. So all we did was to just play with the vectors. And again, the principle that comes up from this is that whenever we have 2 points that define a vector, we can actually write this vector as a sum of 2 other vectors where we interpose a third point. And the third point could be anywhere. This is the principle that we just used. So this is KL plus, I'm sorry, KM plus ML. Okay, we're interposing the point M in here. That's the principle that we used. And let's go to the next problem, which is a much more interesting problem. It says the following. Suppose that U and V are 2 non-parallel vectors. So 2 non-parallel vectors. What does that mean? Okay, the underlying line segments are not parallel, but in terms of the language of vectors, what this means is that one is not a scalar multiple of the other. Let me write this down. So, i.e., one is not a scalar multiple of the other. Okay, that's the bottom line. Because 2 vectors are parallel, if and only if 2 non-zero vectors are parallel, if and only if we can scale one and get the other. So what we want to do here is find the number lambda so that the 2 vectors lambda u plus 1 minus lambda v and 2 plus lambda u plus lambda v are parallel. So in other words, let me try to rephrase this. You start with 2 non-parallel vectors, and you're asking, can I choose a lambda so that these 2 vectors are now made to be parallel? And well, again, we said that 2 vectors are parallel if and only if the one is a scalar multiple of the other. So we would like, for example, this vector to be a scalar multiple of that vector. Here one might ask, is it possible for the vectors that we just took, these two vectors, to be zero, or one of them to be zero? And the answer is no. Exactly because U and V are parallel, the only way to make their this linear combination zero is if both numbers lambda and 1 minus lambda are simultaneously zero, and this can never happen. Lambda and 1 minus lambda cannot be zero. So I'm making this side point, but basically I'm saying that both of these vectors that we wrote down are not zero vectors. So in any case, if we want them to be parallel, then let's say the second one, and it could go the other way around. Let me put my arrows here. Should be a scalar multiple of the first one. So we should have this. And this is where it becomes kind of fun, because here's what is going on. What you need to do here is find a scalar multiple of U and make it equal to a scalar multiple of V. The only way that this can ever happen is if the coefficients in front of U and V are both zero. Again, let me explain this. So if somebody told you that you have alpha U is equal to beta V and ask you, is this even possible? What we know about U and V is that they're two non-parallel vectors, right? And alpha U is parallel to U, and beta V is parallel to V. The only way that you can make these two being parallel is if at least one of them is reduced to zero. Okay. So one of them has to be reduced to zero, and the other could be possibly non-zero. I'm sorry, both of them have to be zero, because since they're equal, if one of them is zero, then the other is zero. So both of them have to be zero. The only way a scalar multiple of the first is parallel or equal to a scalar multiple of the second is if both of them are zero. So alpha would have to be zero, beta would have to be zero. What we need to do is rearrange the vectors, the equation that we have here, so that we have a scalar multiple of U equal to a scalar multiple of V. So let me write this as 2 plus lambda U plus lambda V is equal to T lambda U plus T times 1 minus lambda V. And now let's put the U's together. So we will have 2 plus lambda, sorry, not plus, but rather minus T lambda times U, and take the lambda V over to the other side, and that would give you T times 1 minus lambda times V. So these two have to be equal to each other. And for the reason that we just explained, both of them have to be zero vectors. And the only way they can be zero vectors is if the numbers in front of them are zero. So we should have 2 plus lambda minus T lambda is equal to zero. And T times 1 minus lambda is equal to zero. And now we need to determine lambda. We need to focus our attention on lambda. Okay, so how can we solve this? Well, we can, for example, let's multiply out the second equation, and that will give us 2 plus lambda minus T lambda equals 0. And This will be t minus t lambda minus lambda equals 0. And here we can have a simple solve the first equation for t lambda. So this will be 2 plus lambda, and plug this into this one. So that will give us t minus 2 plus lambda minus lambda is equal to 0, which will give us t minus 2 minus lambda equals 0. And this will give us t is equal to 2 plus 2 lambda. Okay, once we know this, then we can plug it into the first equation, for example, and that will give us an equation for lambda. So we will have 2 plus lambda minus 2 plus 2 lambda times lambda is equal to 0. And this will give us 2 plus lambda minus 2 lambda minus 4 lambda squared equals 0. And this will be minus 4 lambda squared minus lambda plus 2 equals 0, or rather 4 lambda squared plus lambda minus 2 equals 0. And finally, we just have to solve this quadratic polynomial. Actually, I'm sorry, I made an obvious mistake here. I should have said 2 lambda squared. So this is 2 really, it's not 4. Sorry about this. Okay, and we just need to solve this equation. It will have two solutions. How do we solve such an equation? Let's find the discriminant. That's b squared minus 4ac. What is a is here 2, b is 1, and c is negative 2. So this will be 1 squared minus 4 times 2 times negative 2, which is the same thing as 17. So we have two solutions, which are negative 1 plus or minus square root of 17 divided by 2. Okay, so these are the two values of lambda for which these two vectors are going to be parallel. So let's recap. We start with two non-parallel vectors, and we note that two scalar multiples of these vectors can be equal if and only if the coefficients in front of them are 0. Furthermore, if we want these two vectors to be parallel, then one has to be a scalar multiple of the other. So we write this relation, we separate the u's from the v's, we make sure that the coefficients in front of them are both set equal to 0, and then we just solve the system. So this is an exercise that has a little bit of algebra, and it also has the underlying principle that two non-zero vectors are parallel if and only if one is a scalar multiple of the other. And also the byproduct of this, that if you have two non-parallel vectors, the only way that two scalar multiples of them are equal to each other is if the numbers, if the scalars that you use are 0. Thanks for watching.